Hi everyone. In this video you're going to learn how to create what is called a slope field. And a slope field is just a graphical approach to solving a differential equation. Now, why would we want to do this? Well, in the previous two lessons you learned how to solve a differential equation algebraically using separation of variables. The thing is, there are a lot of differential equations that are not separable, so you would not be able to use that method to solve the equation. Here is an example of a differential equation that is not separable. dy dx equals x plus y. We're not going to be able to get y dy x dx on opposite sides of the equal sign. So what we can do, though, is create a slope field. So let's look at how we would do that. All right. So remember, the derivative dy dx represents slope. So what we're going to do is we're going to find the slope at all of these points, and we're going to draw a small tangent line that has that slope at each point. And then the idea is, once you have all those tangent lines drawn, you've created a slope field, and you can look at that slope field and you can actually see the picture of the original equation, the graph of the original equation. You can see it in the slope field. All right, so how do we do this? Well, an easy way to do this is to start with a table of values. Remember, each point gives us an ordered pair. So from each point, we're going to have an x-coordinate and a y-coordinate. And then we're going to find the slope by just plugging in to our differential equation, dy dx. So I'm just going to, do a few of these, and then I'll show you what the entire slope field looks like. But let's just say that we start with, we'll start with an easy point. How about the origin? 0, 0. So if x is 0 and y is 0, and we're adding x plus y, then we're still going to get 0. So in that case, I would want to draw a tangent line that is horizontal, because remember, a horizontal line has a slope of 0. All right, why don't we go now to the point 1, 1. So again, we're adding x plus y, 1 plus 1 equals 2. So at the point 1, 1, I want to draw a tangent line with a slope of 2. So again, I'm just going to do the best I can with that. All right. Why don't we go to the point 1, 2. So again, we're adding 1 plus 2, which is going to equal 3. Because what I wanted to show you is, at the point 1, 1, I just drew a tangent line that has a slope of 2. If the slope is positive, then obviously you want your tangent line to rise from left to right. You want to draw a line with a positive slope. So I do want to draw a line with a positive slope, but I want it to be a little bit steeper than the line that I just drew. Okay. So maybe something like that. Okay, let's find one that has a negative slope just so I can show you. Let's go to the point -2, 1. Okay, because again, if I add -2 plus 1, that's going to give me -1. So at the point -2, 1, I want to draw a tangent line that has a -1 for its slope. So probably pretty close to this one. If we kept going, let's go to -3, 1. So again, if I add -3 plus 1, I get -2. So at -3, 1, I want to draw, again, a tangent line that has a slope of -2. So maybe something like this. Again, drawing a tangent line that has a negative slope but is steeper than the tangent line that I just drew at the point -2, 1. Okay, so you guys, the idea would be you would continue this table for all of the ordered pairs represented by the points, and you would draw your little tangent lines. And once you did that, you would get this picture. So this shows you all of the tangent lines that are drawn. And again, the idea is, and I will tell you, the more points that you use, the better, the easier it is to see the graph of the original function in the slope field. And here we drew the tangent lines at a pretty good number of points, but you almost need it to be a lot more points. I'll show you an example that comes up later in our notes just to kind of highlight what I'm talking about. So like when you look at these slope fields, you can see a lot more tangent lines that are drawn, and so you can kind of start seeing the picture of the graph of the original function, within the tangent line, or within the slope field, excuse me. Okay, well anyway, you guys, I included a couple examples for you to try on your own. So just pause the video and try, because it is a good idea to practice this. Try creating a couple slope fields. All right, so hopefully you were able to sketch these two slope fields. This is what your picture should look like, or pretty close to what we have here for those two problems. Okay, so this is how you actually sketch a slope field. The next thing we're going to look at is being able to match a slope field with the differential equation that you use basically to create that slope field. So there's a couple things I want to point out in the previous three examples that we did. In this, when you created the slope field for dy dx equals x plus 1, if you look at the slope field, there's something that I want you to notice. If you look at the tangent lines, they all have the same slope vertically. Notice how your tangent lines are the same as you look down vertically. See how all of these tangent lines have zero slope? When that happens in your slope field, you know that the equation is only in terms of x. Notice that this differential equation does not have a y, it only has an x. And then the opposite is going to happen. So look at our next slope field. If you look across horizontally, notice all the tangent lines have the same slope horizontally. That's a hint that your differential equation is only in terms of y. Now, if neither of these scenarios are true when you look at the slope field, so let's go back to the x plus y slope field. So notice if you look vertically, the tangent lines are different, and if you look horizontally, the tangent lines are different. So that's a hint that your differential equation is in terms of x and y. Okay, so that can be really helpful when you're trying to match a slope field to its differential equation. Okay, so for instance, you guys, I can tell, let's start with this slope field A. Notice that the tangent lines are the same horizontally. So that tells me we're looking for a differential equation that is in terms of y. So A would have to match with the dy dx equals 2 minus y. Let me go back to my... So dy dx would match with slope field A. All right, let's go to B now. All right, first thing I notice in this slope field is that the tangent lines have the same slope vertically. If you look vertically down the paper, the tangent lines have the same slope. So again, that tells me I'm looking for a differential equation that's only in terms of x. So that would have to be the, well, for right now I'm going to say that's dy dx equals x. Okay, now why is that not dy dx equals sine of x? Well, remember that if we were to anti-derive sine of x, we would get negative cosine of x. And I know the graph of cosine of x is a wave. So I can definitely, looking at the slope field for C, I hope you can see that wave there. Hopefully, and again, the idea is, oops, let me go back to my pen, that if we were to follow the slope field, and think of your slope field as like waves directing a ship or a boat, okay? You know, if these were the waves that were directing a ship or a boat, you know, it looks pretty much like that if I follow my slope field. So I can definitely tell, just because I see a wave, when I look at this slope field, I can tell that that's going to be represented by sine or cosine. So we know that that would match up to dy dx equals sine of x. All right, now by process of elimination, you know, we know that d would match with the dy dx equals x minus y. But let's just say, you know, you didn't know that. Well, a couple hints would be, again, if you look at your tangent lines, they're not the same horizontally, they're not the same vertically. So that would tell me I'm looking for a differential equation in terms of x and y. But again, let's say that wasn't enough to narrow it down. Then I would just pick some points and plug them into the differential equation and see if I actually end up with the right slope at that point. You know, just again as a way to narrow it down. Okay. So what I want you to do is just pause the video and try this one. See if you can match these differential equations to its slope field. All right, so let's see how you did on matching the slope field with its differential equation. So these are the actual matches. But again, some hints would be, honestly, I always like to look for the, you know, whether the equation is in terms of x or in terms of y. So honestly, you know, if I were matching these, I would, let me go back. Let me get rid of that. There we go. The first thing that I would do, again, is look for any slope fields where the tangent lines are the same horizontally or vertically. And so, like, I'm noticing when you look at the slope field B, if you look down the paper, the tangent lines are the same vertically. So that means we're looking for an equation in terms of x only. And luckily, in our choices, we only have one of those. And then I'm noticing slope field C. The tangent lines are the same horizontally. So again, that tells me I'm looking for an equation in terms of y. And again, we only have one. Now, for the other two, I would probably maybe pick some points. An easy thing to do is maybe start where you have horizontal tangent lines. So for instance, let me go back to my pen. I'm noticing in slope field A that we have a horizontal tangent line at the point 1, -1. So if I, you know, with the two equations I have left, the only equation, if I plug in 1 for x and negative 1 for y, the only one I'm going to get 0 for is the x plus y. So that would tell me that that slope field matches with x plus y. And of course, process of elimination, we can match slope field D to its differential equation, but you honestly could do the same thing. Okay, now the other thing I want to show you is, the idea behind drawing the slope field is, can you see the graph of the original function within the slope field? So here, we want to try to figure out the specific solution to the differential equation. So knowing the graphs of your parent functions can be helpful in this case. Are you seeing, when you look at this slope field, which of these graphs are you seeing in the slope field? Well, let's run through these. A is y equals x squared. Now, y equals x squared, the graph is a parabola. So, yeah, I'm not really seeing that shape when I look at this slope field. Okay, y equals e to the x. That's exponential growth. That graph looks like this. Yeah, not seeing that graph. Okay, y equals negative x. Well, that would be the graph of y equals x reflected over the y-axis. So the graph is just going to decrease instead of increase. But again, that's not the shape I'm seeing. Okay, cosine of x. Well, the graph of cosine is a wave. Definitely not seeing that graph. Okay, natural log of x. Natural log of x looks like this. Ah, now I think we have a match. Because notice, if you were to kind of follow, and again, think of these as like the waves in the ocean. You know, which direction are the waves going to push the boat? Hopefully you can see that shape within the slope field. So it looks like our specific solution is y equals natural log of x. Okay, here's another one. The slope field for a certain differential equation is shown above. Which of the following could be a specific solution to that differential equation? Well, again, the shape that I'm seeing in this slope field, if I just kind of follow my tangent lines, I'm seeing this overall shape. Okay, so let's see how well you know your parent functions. What would be the parent function for that graph? Well, hopefully you're saying x cubed. So the answer would be D. All right, you guys. So that's an introduction to slope fields. They're actually pretty easy, and they, can be kind of fun to draw. So we'll definitely practice this some more. But as always, thank you for watching, and have a good night.